Welcome. Today we will be taking a look at the notes worksheet entitled Fundamental Counting Principle. And so the objective of this lesson is to kind of determine how many different ways or how many different possibilities a set of events can occur. And so we'll go ahead and take a look at the mathematics behind that in just a few minutes. It looks like I have a little introduction to counting at the top of your page here. So just getting us sort of thinking in the right direction, I guess. So we'll just write in some numbers here. I have some of the answers, and then again we'll go through some examples on how this is going to play out. So letter A, how many different arrangements are possible on a Rubik's Cube? So not sure when the last time you looked at a Rubik's Cube, but here it is. How many different ways can a Rubik's Cube be arranged? I have 115 trillion, 880 billion, 67 million, 72,000. That is absolutely amazing. So all the different arrangements on a Rubik's Cube, that's how many are possible. Okay, next one, again, just introduction, nothing else here. Letter B, how many ways can you play the first 4 moves in chess? So here's the number that I have, and I'm going 318 billion, 979 million, 564,000. Pretty amazing. All right, so first 4 moves in chess, that's how many different ways you can do that. This is something we would take a look at maybe together. How many ways can you arrange 12 books on the shelf? So you have 12 books, you have 12 spots on the shelf in front of you. How many different arrangements are possible? And I have this number right here, 479 million, 1,600. All right, pretty amazing. And this is a good one, the last one here. How many different Colorado Lotto tickets are possible? I have 5,245,786. So what we are going to be doing is just taking a look at, again, how many ways or how many possibilities are there for an event or a set of events to occur. And the way we're going to do this is through what is called the fundamental, or as you can see on your paper, the multiplication counting principle. And so it says just the fundamental or multiplication counting principle is a mathematical way to determine the number of ways that a series of events can occur. So we're going to go ahead and just lay this out visually and sort of talk about a way for us to do the mathematics. And so it looks like I have a number of examples to kind of back this up. So nice and straightforward to start. If you've seen this before, great. Kind of bear with it. A couple of the harder problems will certainly be on the back side. So anyway, here we go. Josh has 4 shirts, red, blue, yellow, and green, 3 pairs of pants, tan, brown, and gray, and 2 pairs of shoes, brown and black. How many different ways can he select an outfit? Use a tree diagram as a visual aid here. So I guess the way we're going to phrase this over the course of this lesson is there a certain number of events or a certain number of tasks that Josh has to take here. He has to pick a shirt. Then he has to pick a pair of pants. And then he has to pick a pair of shoes. So 3 different things that he's going to do, one coming first, then another one, and then another one. So let's lay out the first task and talk about the number of possibilities for that first task, and then the second task, and then the third task. So everybody, what I'm thinking is 4 shirts, and just do this however you'd like, to be honest, but essentially something like this would do. And he can go either red, blue, yellow, or green, something like that. So red, blue, yellow, or green. And I'm going to try to get this in, and if it gets a little convoluted, my apologies on that. Maybe you can do it on your paper and have it look decent as well. So 4 possibilities for the shirts. Now from that, then has to make a second decision in terms of the number of pants, and in this case he's got 3 to choose from. And forget color coordination here, just going to choose any of the 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3, and again, last but not least, 1, 2, 3. Hope everyone's okay with that. So as you can see, kind of like at the top, you can pick a red shirt and then go tan, brown, or gray on that. Or maybe the blue shirt came out. And if you went blue shirt, then again, tan, brown, and gray, et cetera, there, just kind of working down the line. And as you can see, really 3 possibilities on these 3 branches. tan, brown, and gray. And again, as I said, if you've seen this before and you kind of know how this is going to play out, great. All right, so that was the second task. There were 4 possibilities for the first task, 3 possibilities for the second task, and now the third task, it looks like he's got to pick a pair of shoes, and there are 2 possibilities, 2 choices, either brown or black. And so I'm just going to kind of do this, as I said, not ideal visually, but maybe get a sense of it. So brown or black coming off of each of these. And not bad. Could have been better, could have been worse. All right, so I'm going to go ahead and put mine in. Again, if you don't feel like you need to, that's fine. But brown, black, brown, black, etc., etc. there. You know what? I'm going to kind of dot this, and let's kind of move forward at this stage. But you can definitely see at the third stage there are 2 possibilities that fall into place. Now, if I counted up all the different outfits that are possible here, I would just run my branches. I would go red, tan, brown, red, tan, black, etc., right along the lines there. And long story short, everybody, it looks like you would find that there are 24 possibilities. Okay, we no need to list them. We had the diagram going, and I kind of cut my losses on that at some point in time. Okay. Now, again, you can kind of see it, the way this example is set up, that I asked us to use a tree diagram as a visual aid to come up with those 24. Now what we want to do is come up with what's called the fundamental, or the multiplication counting principle, to kind of shortcut this. And again, if you've seen this before, outstanding. Let's fill this in. 3 tasks that Josh had to perform. Number 1 is to pick a shirt, and there were exactly 4 possibilities to do that. Number 2 was to pick a pair of pants, and there were 3 possibilities to do that. And the third task that Josh had to do is to pick a pair of shoes, and there were 2 possibilities for that. And why it's called sometimes the multiplication counting principle is because if you multiply the number of possibilities for each task, you get the answer. And there's your 24. And so that's how it's going to play out, everybody, is you really have to determine the conditions or the number of ways to perform a particular task. And if there are a series of them, very simply we multiply those numbers together. Okay, good. So again, let's just get a little practice on this piece. Not really too bad. Again, they'll get a little harder on the backside potentially. So let's go with another fairly straightforward one. A cafeteria offers 4 different entrees, 5 different side dishes, and 3 drink options. Choosing one from each category, how many different options exist? Now, I have no intention whatsoever of doing another tree diagram. It got a little chaotic in there, and I don't want to repeat that. So what I'm going to do is just think about sort of the tasks at hand. I have to pick an entree, I have to pick a side dish, and I have to pick a drink. So I just think about the number of ways that I can perform each of those tasks. So when I pick an entree, there are 4 ways that I can pick an entree. Then I have to pick a side dish, and there are 5 ways to pick a side dish, 5 possibilities for the side dish. And then I have to pick a drink, that's my third task, and there are 3 possibilities for a drink. And I do 4 times 5 times 3, and not too much issue there. I end up getting 60 different options or 60 different possibilities for this meal. Okay, good. So 4, 5, and 3. And notice just number of ways that we can do the first task, number of ways we can do the second task, number of ways we can do the third task. All right, let's keep it rolling. Number 3. So we just have to interpret, that's going to be the key, and break it on down into individual tasks. How many ways can 6 true or false questions be answered? All right, so think about this. You're sitting in front of you, and you've got 6 true-false questions, and your first task is obviously to answer the first question. So what I would ask you is task number 1, answering the first question, how many possibilities are there for the first question? And it's either going to be true or it's going to be false. So for the first question, there are 2 possibilities. Okay, now what's your next task? Well, your next task is to answer the second question. And how many possibilities are there for the second question? There are 2 possibilities for the second question. And then your next task is to answer the third question. 2 possibilities for the third, 2 possibilities for the fourth question, 2 possibilities for the fifth question, and 2 possibilities for the sixth question. 6 tasks to be accomplished in order to make this series of events occur. And in each case, there are 2 possibilities to do it. So now, again, all I do is I throw a little multiplication into the mix there, and I multiply the number of possibilities for each task. I'm hoping that makes sense, because as I said, when it gets a little harder, you're going to really want to break it down according to this mindset. Anyway, in this case, how many ways can 6 true or false questions be answered? And it looks like 64. 2 to the 6th, or as you can see, just kind of breaking it down there, 2 times 2 times 2 times 2 times 2 times 2. All right, good. Let's move on to example 4. So radio station call letters in the U.S. consist of either 3 or 4 letters, of which the first must be either K or W. Assuming that letters may be repeated, determine the number of radio station call letters possible. All right, very nice. So I guess here's the idea, and I'm going to write a few things down here. I guess the first thing I see is the call letter, or let me just see how this is worded. So the number of radio stations can be either 3 letters or 4 letters. So I think we're going to have to kind of break it up into 2 different parts there. I'm going to just sort of do this as I interpret. And in this particular case, I think we want to take the number of 3-letter possibilities and then add them to the number of 4-letter possibilities. I hope everyone's okay with that interpretation. So we're going to find out how many different 3-letter radio stations there are. So 3-letter radio stations, and then how many 4-letter radio stations there are possible out there, and then we would add them together. What we're going to see as this comes up more and more over the next several days, or when you talk about counting, typically means addition. So what we're going to do is take really the number of 3-letter possibilities and add it to the number of 4-letter possibilities. Okay, so let's go ahead and do that. So let's talk about the number of possible 3-letter call letters, if I'm phrasing that correctly. There are. How many possibilities are there? So I guess the first thing is to meet the conditions. Always make sure you've met the conditions. And it does say right away that the first letter must be either K or W. So in terms of the 3 letters here, looking at the first task is to figure out how many possibilities there are for the first letter. And there are 2. It has to be either K or W. Now there are no conditions on the second letter, and repetition is allowed. We'll talk a lot about that over this unit, repeating, not repeating, and so forth. But repetition is allowed, and so what I'm seeing is that second letter can be any one of the 26 letters in the alphabet. Okay, good. And then there's the third letter, of course. So my next task is to figure out how many possibilities there are for the third letter. And again, there are no real restrictions or conditions on it. It can be any one of the 26 letters in the alphabet. Okay, so if I multiplied these together, this would be able to get me the number of 3-letter radio stations. Okay, now the 4 letters, same deal. It's either going to start with a K or W, so let's go ahead and throw in a 2 right there. First letter must be one of those 2, K or W. Now the second letter, as I kind of look to this, can be any letter. The third can be any letter, and the fourth can be any letter. And so as a result, I get a calculation that looks something like this. Tasks at hand, in broad terms, find the number of 3-letter call stations, or radio stations, excuse me, and the 4-letter radio stations. All right, so this is the number of 3-letter radio stations possible, and this is the number of 4-letter radio stations possible. All right, let's bring up the calculator. I'm going to need that here to kind of work this out. And so I got 2 times 26 times 26, and then I'm going to add the number of 4-letter radio stations possible. So make sure I get this right. And there we go. And I hit enter. And so that, I believe, is our final answer there. I'm getting 36,504 possible radio stations. Okay, good. Now we're going to get a little more formal with this, but I think we've set the precedent nicely there. I'm hoping these examples make pretty decent sense. Let's move on to the next piece. So this is what I was thinking in terms of formalizing it, really making sure that you interpret the problem and organizing into what is called a slot diagram. So let me just read what's on your paper and then we'll kind of go for it. It says slot diagrams help organize information before applying the fundamental counting principle. Be wary of special conditions that can affect the number of ways we can perform various tasks. So I think we had been doing this intuitively, but this is a more explicit way to kind of put this together. So I kind of identify the first task, and I figure out how many ways I can do that. Then I identify the second task or the second condition, and I figure out the number of possible ways I can do that. And I just keep doing it until all of the conditions or all of the tasks have been accomplished. Once I've done that, then we apply the fundamental counting principle. All right, let's do the last couple here. So example 5. In order to open the teacher's copy room, a person must enter a four digits from 0 through 9 in order. How many possibilities are there if repetition is allowed? So you walk up to the copy room, and there's a little push button there, 0 through 9. You're going to press 4 buttons. How many possibilities are there? So if repetition is allowed, let's kind of think about it and identify your first task. So your first task, of course, is to hit the first button. And how many possibilities are there? Well, 0 through 9, everybody. That's 10 digits. There's our base 10 number system, of course. So there are 10 possibilities for the first one. All right. Identify the second task, everybody. The second task is to hit the second button. And in this case, how many possibilities are there for that second digit? There are 10 possibilities, of course. It can be 0 through 9 because repetition is allowed. This one does not affect this one right here. Okay, next one. Your next task is to hit the third button or find the third digit. And so in this case, how many possibilities are there for that third digit? There are 10 possibilities. And then last but not least, we want to go ahead and do it one more time. Hit that fourth button, and there are 10 possibilities for it. And so you can see, without too much issue on this one, it looks like 10 to the fourth. So there are 10,000 different copy codes that are possible there. Okay, wonderful. Now the next one, it does say how many possibilities are there if repetition is not allowed. So if you know that the copy code does not have any repetition, so all the numbers are different, how many different possibilities are there still out there? So let's go for it. Again, identify the first task, and so the first task for me is to hit that button. The first time, enter the first digit, and there are 10 possibilities for the first digit. Okay, now, I know that the second number is different than the first. So my second task is to type in or hit the second number, but I know it's different from this, and so what that means is there are only 9 possibilities left. So whatever was the first one is now out, and there are only 9 left. Okay, now there are 2 that have been taken out of circulation. So when I go to hit the third button, or the third digit here, I know that there are only 8 possibilities left. And then you can kind of see the pattern here. My last task is to hit the fourth digit, and in this case, I know that 3 have been taken out of circulation, and so as a result, there are only 7 digits left. And so I would do 10 times 9 times 8 times 7, and I'll go ahead and grab my calculator and bring that on up. And so when I do exactly that, 10 times 9 times 8 and times 7. And I get 5,040. Okay, so in this case, I identified the number of tasks, 4 tasks, type in the 4 digits, and how many possibilities for each of those 4 digits. In the first digit, there are 10 possibilities. Then this is the key, only 9 possibilities for the second digit because it has to be different than whatever the first digit was. right down the line. Okay, how about letter C? How many possibilities are there if the first two digits are odd and the last two digits are even and there is no repetition? All right, so you've really narrowed it down, and these are the conditions that you know. How many possibilities are there for this situation? So again, your first task is to enter that first digit. That hasn't changed. And so there are some conditions to that first digit, though. You know that that first digit has to be odd. So it's either going to be a 1, or a 3, or a 5, or a 7, or a 9. And so that would be 5 different possibilities. Okay. Now the second task is to enter the second digit. And of course, second digit also has a condition to it. Number 1 is it's odd, and it can't be the same as the first one. So whichever odd number this is, this one has to be a different odd number. And I'm hoping you would agree then that that only leaves 4 odd numbers left. All right. Third task, everybody. Let's get a slot in there. Third task is to go ahead and type in the third digit. So let's think about what we know about the third digit. Looks like we know it's even. And obviously it's not going to be one of these. But in terms of it being even, it could be either 0, or 2, or 4, or 6, or 8. And so that, sorry about that, there we go. And so it's going to be, did it again. Okay, let's see if we can get this to work. It should be 5 possibilities, as I said, 0, 2, 4, 6, or 8. And then the last one, of course, the last task is to enter that last digit in. And how many possibilities are there in this case? Well, you know it's even, and it can't be the same as this one. So whatever this one is, it's now taken out of circulation, and there are only 4 possibilities. And so we end up doing 5 times 4 times 5 times 4, and we multiply those together, and it looks like that would give us 400 total. All right, good. So I like those slot diagrams. It's a nice formalized way to pull this off. The key is really identify the tasks or identify the conditions. All right, last one here. Let's go ahead and do example 6. So let's see, professor is teaching a psych class of 10 students. She has a visually handicapped student, Louise, who must sit in the front row next to her tutor, who is also a member of the class, so also one of the 10 students in the class. If there are 6 chairs in the first row, how many ways can the professor assign students to sit in the first row? Okay, now it's getting harder. So let's kind of think about this again in terms of the number of tasks and identify those particularly. Now I'm going to go ahead and just throw the 6 seats in the front row here. So let me do that first. It doesn't mean that I'm just going to sort of go 1 seat to the next, to the next, to the next. What I want to do instead is really talk about the tasks at hand. So let's identify the tasks. And so let's see sort of the conditions there of this problem and then see how many different ways we can pull this off. Okay, so let's go for it. So I think the key to this is that Louise and her tutor, out of those 10 students, Louise and the tutor, must sit in the first row. So I would argue, kind of looking at this, our first task at hand is to figure out how many ways Louise and her tutor can sit in their 2 seats. So if you want, I think that's not a bad idea to write this down. So number of ways Louise and the tutor, excuse my shorthand there, can sit in their 2 seats. I think that's a good way to start this, as that is really the primary condition to this problem. So that is the first task at hand, is to figure out how many different ways Louise and the tutor can sit in their 2 seats. So I'm going to kind of break this up into 2 different parts, but let's see if we can get this to work. So the key is she is a visually handicapped who must sit next to her tutor. Oh, that's the key. Okay. So right there, Louise must sit next to her tutor. So what that now enables us to do is start focusing in on where they can sit. And so let's kind of talk this out a little bit. I would argue that Louise and her tutor can sit here. They can sit in these two seats. They can sit in these two seats, these two seats, and these two seats. I'm hoping everyone's okay with that. Just figuring out the two seats that Louise and her tutor are going to occupy. It looks like there are 5 different possibilities, the 5 that I circled. Now, here's the thing now. Once they're in those two seats, well, I should say they're not in their two seats just yet. Once we know which two seats they're going to sit in, now we have to get them down into their individual seats. Because say we know Louise and her tutor are going to sit in these two seats right here. Is everyone okay seeing that? Well, basically it could go Louise and her tutor or tutor and Louise. Is everyone okay with that? And in each case, once we know the two seats, it could go Louise and the tutor or tutor and Louise. So what I have here is 5 different pairs of seats. That's what I circled. And within the pair, there are 2 options, Louise tutor or tutor Louise. So here's what I'm coming up with, and I put it together. If you want, you could kind of separate that out into a 5 times 2. But I'm seeing that as 10 different ways that Louise and her tutor can get in their 2 seats. Now, if the verbal explanation and even the drawing doesn't work, please ask questions on that. But I think this is the key. All right, so let's pause for just a second and kind of make sure we see that. So just one more time, everybody. So 5 different pairs of seats for Louise and her tutor. And within those 2 seats, there are 2 different possibilities. And so we do a 5 times 2, which is 10. Okay. Now the main condition of the problem is set. So now we go on to our next task. And we just kind of figure out, well, how many ways can the next seat, I guess this would be the 3rd seat out of the 6, be occupied. So if you want to write it down, I think this was the key. So I wrote this down, but I'm not going to write it here. I guess this would be the number of ways the 3rd seat can be occupied. Because 2 are taken with Louise and her tutor now. They're done. They're out of circulation. And what I would see in this case, if you look at the problem, there were 10 students. Louise and her tutor are 2 of those 10, so there are 8 students left. And so for that 3rd seat, everybody, I'm getting 8 possibilities. All right, next one. So now basically out of the 6 seats, you've got Louise taken care of, you've got the tutor taken care of, you've got 1 other student taken care of, 3 seats left. So this would be for the 4th seat, just something like this, give or take. So the 4th seat, and I'm seeing that there are only 7 students left to occupy that 4th seat. Now the next task is to get somebody in that 5th seat. 4 people down, 6 left. And then last but not least, the 6th seat. Looks like I've got 5 people down, 5 left. And I think that does it. So it's very hard to kind of really interpret the problem and make sure you meet those conditions. That's the key. All right, I'm going to multiply them together and put my answer on. So here's what I have. It looks like 10 times 8 times 7 times 6 and times the 5. And that's our answer, 16/8. So how many different possibilities are there to get students in the class into that front row? There's your answer. Fundamental counting principle, as you can see, pretty hard because of this condition right here. We satisfied this task, then we go on to the next task, the next task, the next task, etc. Okay. You'll definitely just kind of get some practice on this and work it through. But try to break it down as best as possible. Identify the tasks. That's the key. How many ways can each task occur? And if you can pull that off, you multiply them together, and I think you've got a nice final answer. Hey, thanks for listening. Check answers, of course, and let me know if you have some questions along the way.